Right, so thanks for coming. It's just a few of you, but it's really appreciated. I know that some of you have questions that I'd like to address at the end of the lecture. Before then, I'd like to go for a couple of examples here. Exam-like examples, exam-like problems. So I think you have a pretty good idea on what the exam will be, just looking into past papers, because there's a lot of variety and a lot of examples there. It won't be that different. Okay, so my suggestion is go through that papers, go through the examples we went through during the lectures, make practice based on problems you find in books, in the main books, the first one or two, in the reading list, for example, the Schwartz book, and the, the Rappaport, maybe an alternative one, or the Goldschmidt as well. So, concerning a quick note, since I'm recording, concerning the coursework, I'm really pleased about the performance you had in the coursework. It was an excellent one. It was difficult to give something below 70, really. So you shouldn't worry about that. And get in touch with me concerning the marks. As I said, I don't like Moodle. And that's, I'm recording these for everybody. I don't like Moodle because I can only give just one number at the end. You may want to have feedback, and you may want to know what is the distribution of these marks across the various fields in the mark scheme. Okay, as some of you have pointed out, it's interesting to know in order to avoid repeating errors in the future. That's the purpose. So giving just one number, it's meaningless to me. Okay, and probably to you as well. So just drop me a line, and I can give you the mark, and I'm happy also to copy-paste the distribution of marks across all the fields, okay? So that's one thing, and having said that, of course, those of you who are MOC and are going through the project shouldn't be too worried, because if the diligence and level of sort of technical detail is going to be similar to the coursework, then you don't have problems at all. Okay, just try to be sort of a bit more inventive in the project. You have to cover a full project, which is a very good exercise. Some of you will go out there to work as a telecommunication engineer. I've been talking to one of you earlier, who's going back to China to work for Huawei. So it's really taking part to the excitement now that will happen in a couple of weeks concerning 5G. So it's important, to do this. And that's why we keep this coursework element in this module. It may be annoying, it may be not very well defined, but the way I like to do it is to keep it open, to keep it flexible for you, right? So do that with the project as well. Try to be inventive, I posted a couple of examples for your convenience. You can, of course, go along that line, and it will be a good course as soon as you, or as long as you understand all the content you put in it. But try to vary a little bit. That's my suggestion. And it's a chance to sort of start from what we covered in the lecture and maybe go into the professional literature and expand your knowledge. That's the way I see this project. Okay, so don't have fear to write things wrong. It's impossible to write something wrong. It's just you maybe tackling something a bit more advanced at that stage. You have a very large foundation knowledge now on mobile communications that gives you access to the technical literature and the scientific literature. There is the practical thing of the exam. Of course, you're thinking about marks, you're thinking about performances. That's fair enough. For this reason, we are here. And I'd like to offer, as I said, a couple of examples, give you the chance to solve them, give you elements of solutions that you already have. As I said, it's going to be very similar to the past papers, but in case you didn't tackle them, at least a couple of very common problems can be seen here in greater detail. And at the end, as I said, I will reserve some question time where I will wander around and ask your questions about project and exams and all the things that you may have. For this reason, I would have preferred that most of you have attended today, but anyway, you can always get in touch with me via email. Okay, so the first the first problem that I'm offering is actually concerning error correction in here. So the exam will be, as you know already, should you have questioned yourself what is the mark distribution, etc., and you went back to essentially the past papers, you know that there is essentially typically a main question at each section of the question. That's an entire question, you know, it's actually covering more than one slide. The first part will be A, second part B, then will be C and D. And for every section here you have subsections, and I give you mark to the detailed subsection. That gives you a lot of flexibility, and typically is a way to sort of pick up all the detail you put in the answer. Sorry, it came out badly, but that's just a matrix with the ones and zero in there. So the first one is, you remember the Hamming bounds. We went through the demonstration on these Hamming bounds in here. So you know for block codes how you need to design or how you need to distribute parity bits given a certain number of errors that you want to correct. Okay, so the question may be for t. If t is the symbolic variable and used for the number of errors, you know, the first question will be how many bits do I need in the code word to have t equals 3, for example, and I decide concerning my bandwidth requirement that I may use 6 check bits, for example. Okay. The second one is how many information data bits does any code work have for we scale down to t equal 1 if there are still 6 check bits. So yeah, you need to remind yourself about essentially the Hamming bounds typically. And then apply in order to find the answer to that. And then, the second part will be something still related to block codes, but unrelated. They're not necessarily connected, of course, and that's why we divide up questions into sections. Okay, so the subsections are, of course, related to the main section, but one section is different to the other. You know, it's typically belonging to the same subject in a way or another, but it's different in terms of mathematical tools that you have to use. Here, for example, we talk about the generation matrix here. The generator is reported here. It's a 6 by 3, as you can see here, and you have to calculate the code words. For this, you're actually given a table here, and you have the data bits. With 3 bits you actually can have all these 8 combinations, and from there on you can calculate the code words given the generator matrix, and then you have to calculate the Hamming matrix, you know, the transformation between the two, and actually use that to calculate the syndrome mean and then detect an error, if any, in the received data as I'm giving you 110101. I'm sure we went through examples like that already, but you see it's a month away from the last lecture. We've done that probably halfway through the module, so a lot of time in between, so certainly you need to remind yourself about the main formulas. Okay, so last part may be still about coding, but not about block coding here. In fact, what we actually do here is put down a convolutional encoder. You know, what is the output sequence for an encoder like that? Again, something we tackled in the lecture. Okay, but again, there are rules that you have to follow. How you distribute the bits as the input data enters the shift register, for example. Then you freeze the position and you calculate the 2 exclusive ORs that give you the 2 branches in output here, and this is your code word. You know the input sequence is 1001 here, so I give you full detail. And you may always ask questions during the exam. I'll be sitting in my office ready for you to answer questions. Okay, should you have any difficulty. So this year luckily enough, I don't have travels. At the last year I was on travel, unfortunately, for a conference, so it was a bit more difficult. This year I can actually answer your questions. It doesn't mean that you can ask, a million questions during the exam, but if there is something that is obviously making you uncomfortable, or most of you uncomfortable, then the personnel there will take care of any question and will get in touch with me. Okay? Good. So what I propose now is, first of all, why don't you try to solve the first two sections in here. Okay, let's start with section A. Okay. Try to have a go, and then I will offer my answer after, say, 5 minutes. Okay? You don't need to give probably the full answer, but just to address the problem, and if you know what you're doing, then we can actually see whether this is correct or whether you're not in the right track. Okay, so I'll give you 5 minutes. Okay, in the meantime, I obviously pause the recording here, and then I'll be back to the recording to actually show the correct solution here. Okay, so the suggestion is go back to the Hamming bounds. In the exam, you look at, okay, you have a lot of knowledge, you sit down there, you see these questions, and at the beginning you don't know what to do, of course. Then you relax, you go back with your mind to what is the question, essentially, the question elements that needs particular addressing. In this case, the tricky bit is remembering the Hamming bound. Once you spotted the topic, then you go back peacefully to the formula, you write it down, and you try to give an answer. And be careful to substitution of numbers. This is actually the tricky bit where you expedite and you can make errors in there. Okay, we can try to give a solution here. In the first part, this is sort of exam-like problem, again similar to what you can find in past papers. Question is asking you to essentially quantify bits in a block code for a given number of errors that you want to correct, t. Here, particular t equal 3, t equal 1, part 1 and 2. Here, once you've done part 1, part 2 is actually easier. That's why you get more marks in the first part and less mark in the second part. And typically I also give marks to intermediate passages within the subsections. Okay, I don't just go for the full mark. Okay, so what you need to do for A, essentially, is, as I said, first of all, remind yourself about the Hamming bound. So that's what you need to have in mind. We demonstrated in the lecture that if I have a block code of length r equals 6, or sort of r in general, sorry, and the number of errors that I want to correct is t, and the number of bits and the total block code needs actually to be satisfying an equality like that, 2 to the r is greater and equal to, that's why it is called an upper bound, I 0 to t, then you have the Newton binomial and I here. In our case, as I said, r is equal to 6, t is equal to 3, and so it's a non-trivial development of this inequality here. So 2 to the 6 greater equal than sum from I equals 0 to 3 and I okay, so if I unfold here, the second member, the right member, is actually equal to n factorial over 0 factorial n minus 0 factorial plus n factorial over 1 factorial n minus 1 factorial plus n factorial over 2 factorial n minus 2 factorial plus n factorial over 3 factorial n minus 3 factorial, and this was the last term. So I just unfolded this summation. In here you see it's quite involved, because you have loads of factorials, etc. But as you calculate them, you see that essentially, typically the trick here is to simplify the numerator with the numerator factorial with the denominator factorial, as you know. So you're left with just the last 1, 2, and 3 terms respectively of the numerator over the scaling factor that comes from the number of bits corrected in here. So eventually, if you unfold, and that's already, for example, if you get it right, and that's already 2 marks out of 5 in here, okay? So that's the way it works. I'm going to give you a ready mark for having remembered the inequality or the equation and having addressed the problem in the right way. So it's not a binary thing. You either do the final result or not. No, it's just a private thing, which I, by the way, keep as much flexible as possible, okay? So this will be 1 plus n, okay, so the second term will be n. Yeah, 0 factorial is 1, so you're left with n factorial over n factorial, which is 1. That's n factorial over n minus 1. So essentially, if you develop these will be n times n minus 1 times n minus 2, etc. These will be n minus 1 times n minus 2 and minus 3, etc. So you cancel out all the terms but n. Okay? Is it clear? Good. And we go along with this reasoning, and we get actually n minus 1 at the numerator over 2. And the tricky one is the last term here that has loads of products, terms, and eventually boils down to n times n minus 1. Let me write it this way. N minus 1, n minus 2 over 6, which is 3 factorial. Okay? So you now develop all the terms in here. There will be 1 plus n plus n squared over 2 minus n over 2 plus you have n squared minus n times n minus 2 over 6, which you can further develop in here. If you get to the right answer, which is eventually equal to 1 plus n cubed over 6 minus 3n over 6 plus 2n over 6 here. Yeah, this level, if you set the C for the calculation, I give another 2 marks out of 5. Okay, this has been motivated by the fact that you need to remember how to unfold the factorials, etc. And yeah, eventually that will give you probably a better place to give you the full sub marks, 2 out of 5. Give the final result 1 plus 5 over 6n plus n cubed over 6. Okay. Right, so at this point, if you multiply, you go back here, and you see that you started with 2 to the 6 here, then you have 2 to the 6 greater or equal than this final answer here, which you get after a few algebraic passages here. Then you can multiply both the members by 6, for example, to simplify, and then what you would have is 6 times 2 to the 6 greater or equal than 6 plus 5n plus n cubed here, and then eventually you need to solve the following inequality: n cubed plus 5n plus 6 times 1 minus 2 to the 6 less or equal than 0. Okay, or n cubed plus 5n greater or equal than 6 times 1 minus 2 to the 6, which is calculated to 378. Here now you do just a substitution of numbers. Okay, so you have essentially r equal to 6. Okay, so you can start, for example, to n equal to 7, right? So we know from the input that r is equal to 6. So we can try n equals 7, and we see that actually we already meet the inequality. So you can firmly say that n must be greater or equal than 7, which is the answer. Okay, doesn't make sense to go to 8. You already meet the inequality, so that's the answer. Yeah.
From where the 7?
Sorry?
7, from where you get the 7?
Because you start with r equals 6.
Okay.
Right?
Yeah.
And the n is the total length of the block code. You remember?
Yeah. So plus 1.
So you start with the integer after r equals 6. Yeah. So that's a natural choice. If you don't need the inequality, you go ahead. N equal 8, n equal 9, etc. until you meet the inequality. Okay? So this, having done this substitution, this consideration will be 1 mark out of 5, for example. Okay. So, yeah, for the second part in here, where t is actually equal to 1, things are easier. We keep r equals 6 here, so we just have 2 to the 6 greater or equal than 1 plus n here, which is n less or equal than 2 to the 6 minus 1 equals 63 here. So the number of information bits which you're asked is actually given by 63 minus 6, which is r in here. 63 is the total length again. R is equal to 6 is the parity bits, the number of parity bits, r. So the information bits is 63 minus 6, which is 57. Okay, and this is worth 2 marks out of 5 because it's a very quick calculation. Okay, so do you get the flavor of what you need to do? Okay, it takes a bit of patience in this kind of, but I took a very mathematical one, I must say, where the number of, probably the example, these with the generator matrix are the true examples where you need to do more calculations. Yes?
Sorry, you've done 63 minus 6 at the end there, how common is it?
Yeah.
It's t equals 6.
T is equal to 1.
Oh, t is equal to 1.
R is the number of parity bits is equal to 6. Yeah.
Is that why you take it away from 63 at the end?
Yes, exactly. You remember this large block, have in mind the structure of the block code. Is a large block of length n, right? And then you have a first part of information bits and a second part of parity bits, which is equal to r. Okay, so we're subtracting this r from the large block, essentially, and you have the information bits.
Sir.
Yeah.
Could you please recheck the fourth and fifth line? Did you make a mistake in the calculation?
I may have done.
I think M should be less or equal than 7. Now.
Oh yeah, of course, of course. Right, yes. Yeah, very well spotted actually, because we have this inequality in here, right? That now has become less or equal, right? So you need to meet these inequality that gives you less or equal than, oh sorry, there is a problem. Okay, let's see, right, I hope it's back in. So less equal, okay. Okay, good. So you can have a go at part B now. Okay. Part B, we've done, I think, extensive number of examples in the lecture already, but I appreciate that if you want to go through it on your own, it may take a bit of thinking. Okay. Okay, so the first job we have to do here is to create the code words. So we'll have, yeah, as I said, you need to make the mental link between having the generator matrix and getting the essentially structure of the code that you have. 6 by 3 means eventually that you have information bits that are length 3. Okay, so you're suggested about that, as you notice this already in the solution, in the question, sorry, itself, which is here. I already arranged the code words or the information bits in the right way, waiting for the code words in here. And you also ask for the minimum Hamming distance in here. So the code words that we have are actually going to be here, 0, 0, 0, 0, 0, 0 here. So 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. Then you have for 0, 1, 1, 1, 1, 0, 0, 1, 1. Okay, then reading off again the generator matrix, you have 0, 1, 1, 1, 0, 1. Oh, sorry, you have 1, 1, 0 actually. Again, yes. 1, 0, 0, and you have 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1 here. Then the Hamming weight here is actually equal to 0 for the first one. Then you count 3 ones in here, 3 ones in here. Then you get 4, 3, 4, 4, 3. Okay, so the minimum distance, as you can see, d min is equal to 3. Okay. And remember you that the code words are actually given by, if we call the message here M, then the code words C, or yeah, let's stick at the notation D here, as you call them. The code words C are actually equal to D times G, where G is the generator of matrix, and you're given that. Yes?
Yeah, is that minimum distance not taking into account the 0?
Well, 0 is not really.
It's already applicable.
It's the minimum Hamming weight, essentially, you know, greater than 0. Otherwise, with 0 you can't correct anything, essentially. Yeah. How do you generate the code words D times G? So you have to do these multiplications where you need to be careful and actually apply the exclusive OR in the right way. So that's where you need a bit of practice. Okay, I can't help much there other than saying you need to go through past papers and past examples that you went or you came across during the lecture. Yeah?
Line number 3, is it 0, 0 or 0, 1? Line number 3.
Oh, that's 1.
0, 1, 1?
1, 1, 0, 1. Let me check. Yes, 0, 1, 1. Yes, sorry about that. Okay. Yeah. Then the second part, of course, is you're asked to calculate the Hamming matrix in here. Okay. So, okay, the Hamming matrix, we're part B, section 2. N is equal to 6. K is equal to 3. Okay. So you need to remember here what is the structure of the generator matrix, right? So generator matrix is actually divided into a permutation matrix, which is given by essentially K times N minus K, so it's 3 times 6 minus 3 in here. And the second part is just the identity matrix, dimension 3 by 3. Okay, so you can look into the structure of G, right, and embed the permutation matrix straight away. Yeah, so the permutation matrix now is equal to 1, 1, 0, 0, 1, 1, 1, 0, 1, and of course I, the identity matrix here, is equal to ones only in the diagonal. Okay, so gluing them together, you should recognize then the generator matrix. Okay. Or in other words, if I look into that, you see that here you get exactly the identity matrix here. So what's left is the permutation matrix in here, okay? Which is 3 times 6 minus 3, 3 by 3. In this case, it's kept low, you know, to make it handleable in an exam. Okay, so now we have P, and we can get started with all the procedure to calculate the Hamming matrix, okay, which is pretty straightforward. Some of you may remember that. Do you want to try to suggest me what to do with the permutation matrix in order to calculate the Hamming matrix H? You want to try to give me a structure. It will be, again, a 2-block, 2-sub-block submatrix structure, and I can give a hint that here I would have an identity matrix again. Why don't you try to fill in the first part for me and suggest me the dimension of the identity matrix? What's going in there? Do you remember? It's the transpose of the permutation matrix, Okay, and I has dimensions n minus k times n minus k, of course. Okay, so eventually, or in our case, reads 1, 0, 1, so you exchange rows with columns to get the transpose. 1, 1, 0, 0, 1, 1 here, and the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. And then you got to the Hamming matrix now. Yeah, this is fundamental, because from there on, now you have the tool to calculate the syndrome and apply the syndrome to the given input. What's the syndrome? Do you remember that? Do you remember the formula to get the syndrome? Syndrome S is equal to R, so the received vector, dot H, the Hamming matrix, transpose. Okay? You need to remember those formulas, guys. Okay, so that's important.
Which formulas?
These one, structure of G. You can't do anything. It's very simple to remember these. Okay, so you take whatever is not an identity matrix and you have a permutation. Then you have to transpose it, complete it, and you have to multiply each transpose by the received vector. So it's something that is extremely straightforward. Okay. I pointed out that already during the lecture, okay, that you need to know what to do here. So I hope it doesn't sound new. Okay, good.
I understand you're supposed to give us some sort of formula sheet in the exam. What kind of formula?
I give you hints for what you don't need to remember. Okay, in every question. So have you looked into the past papers at all?
Not thoroughly.
So you'll see there that there are hints that guide you towards the answer, but of course you need to remember the main formulas in there, but they're just simple and countable. They're not an infinite number, that's not a mathematics course. But you know, you need to, for example, we went through the Hamming bound. If I can tell that to you, yeah, what you need to remember here, one of the few formulas to remember is this one, which is relatively simple. And then you develop, and yeah, most of the marks and demonstrated goes into the algebraic calculations, basically, and just to try to help you there. So you're given this input now, R. So what do we do? Okay, let me write it down explicitly. S is equal to, it's good that we go through that, so it's a way to establish that you need to remember at least this bunch of formulas here. Okay, so S is equal to our given input, which is 1, 1, 0, 1, 0, 1 here. 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. If you've done everything right, that's essentially H transpose here, and that's the received vector R. Okay, it's a multiplication between the two. I leave you the details. So in this case, it will give actually 0, 0, 0, and then you need to interpret that. Okay, what does it mean? Okay, just one quick half a line comment on that. Okay, whatever it is. In this case, what is that? You know, we get 0, 0, 0. It can be different, but in this case, what does it mean? Sorry?
We receive a code word.
We don't have errors, right? We don't have errors, so we receive the correct code word. So there are no errors. So what you should be writing here is that there are no errors, because this is what syndrome is for, to select errors, okay, to tell you what are the wrong bits. Okay, so that was an example in here. Yeah, I hope it is reasonable. What I will give you, talking about the question concerning formula sheets, formula sheet is typically too scary. I try to give hints as much as possible, but I do give actually a couple of sort of tables. One is, of course, the error function, which you can't remember. And those parts of the module that are unreasonable are actually mostly related to this error function and to the blockage probability, if you want. Okay, so having the traffic or the capacity and blockage probability, the way they are related. So the Erlang function is actually given, it's a bunch of numbers. Okay, so my suggestion is try to learn very well how to use the Erlang tables there, okay, and how to use the error functions for failing probability of error, okay, in that case. Right, so we could go now to part C. Let's say it, which is this one. Now we change codes, okay, it's a convolutional code. Do you want to try? This is quite quick. It's an example of essentially a problem where you don't need to remember, can I say anything? Okay. You just pick up the input and you let it work with the structure you're given. So you're asked to write down the output, okay, assuming that the initial state of the encoder is 0, 0, 0, of course. Okay, so try to do that in a few minutes and I'll give you the answer. Okay, good. So let's try to solve this problem. We have in figure Q5 here a k=3, so 3 position encoder, convolutional encoder with 2 outputs and 1 bit, so 1/2 k=3 convolutional encoder. What is the output if we put as an input 1, 0, 0, 1? Yeah, so the first bit to enter is 1, then 2 zeros and the last 1. Yeah, initial set state is 3 zeros in the register in here. So this is actually going to be pretty straightforward. So as a 1 enters the register, now the state is changed and would be, so if you put register state here, that would be 1, 0, 0 in here. Okay, so now I need to apply the exclusive OR here. If you go back to the structure, I'm summing up all the 3 bits for the first branch and just the first and last one for the second branch. So what I give here is the output G1 here is actually 1 exclusive OR 0 exclusive OR 0, which is actually equal to 1. G2 is equal to 1 exclusive OR 0 equal to 1. Okay, so those are the 2 bits that result as an output on the first input bit. Okay, so second input bit here. So there was a 1 entering, now there is a 0 entering. Here will lead to 0, 1, 0 in here, and G1 is equal to 0 exclusive OR 1 exclusive OR 0. here, which is equal to 1, G2 is equal to 0, exclusive OR 0, which is equal to 0. Here, those are the next 2 bits as an output. Then we have another 0 entering the register here, and everything shifts to the right. So I get 0, 0, 1. G1 will be 0, exclusive OR 0, exclusive OR 1, which is actually equal to 1. G2 is actually equal to 0, exclusive OR 1, which is equal to 1. Those are the next 2 bits here. And finally, 1 enters the register in here, which brings the state to 1, 0, 0 here. State is similar to the beginning 1, so I get again G1 to be equal to 1 and G2 to be equal to 1. Okay, so the sequence here eventually is 1, so output sequence is 1, 1, 1, 0, 1, 1, 1, 1. Okay. In terms of distribution of marks, what I give is actually for the first bunch of calculation, I do 2 out of 7 here, because you know how to get started and you carry on the first calculation. Then I go along with 1 mark per passage here, which is 1 out of 7, 1 out of 7, 1 out of 7 in here. And the last one, of course, gluing together the sequence is 1 out of 7 in here, which is basically a bonus mark if you want. Okay, you've already done calculation there. Yeah.
Is the register state always 100?
What do you mean with this question?
When you, for the at the very start of the problem, you've got 100.
Yeah.
Is that just standard what you always start?
You start with 0. The input bit. So I
okay,
should have written. Yeah.
You go with 000 and then you put a 1 in.
Yeah.
Okay.
Depends on the input bit. If it was 0, yeah, of course. No, I mean your question is actually good, because at some point it will always be 100, because if you start from 0, you're locked to the initial state and there's no point in going ahead. But as soon as 1 arrives, it's actually always 100 as a beginning. Yes, which is a good consideration actually. Yeah. So you make have those 7 marks in this way in here. Okay, so you see, this is pretty straightforward again. Okay, so I think all we covered, with the explanation was actually around 1 hour, right? But of course, it would take 20 minutes if you do that straight away without any explanation, which is commensurate. You need to go through actually 4 problems in full. You have 5, you can choose 4, you can do all the 5, and I pick up the best 4, etc. But you have 2 hours to do that. Okay, so it's actually a lot of time. It's half an hour per problem if you really stick at the 4 you think you can do best. Okay, so there's plenty of time. You see, that's commensurate. It's 1 hour from my side with explanation and pauses, etc. So half an hour, 20 minutes is more than enough to do all the 3 parts of this. Okay, so C, B, 1, 2, and A. Okay, so we can actually carry on with another example, one I like particularly. Okay, which is this one, coverage, in here, right, and frequency reuse is, again, a dedicated chapter. That's the entire equation here. These plus, and actually a grid that I give you. I suggest you to redraw this grid or part of this grid in the script itself. No, sorry, not in the script itself, but in the exam paper. here. If you write things in here, hand in the script as well, okay, with the annotations, and I take care of that. There's no problem, but you know, just to avoid any confusion, will be probably better. So yeah, it's fairly straightforward indeed in here. I'm asking what is the pattern of the 7 reuse, which is typically adopted in the UK, in a grid like that. Okay, so you have 7 frequencies to distribute in an hexagonal tessellation. We went through a way to do that. It's an intuitive way, but it's actually very good to maximize the distance between frequencies, therefore reducing interference. So then you have to assume only first tier interferer contribute to the interference and estimate the path loss exponent for a signal to interference ratio of 5 dB. Yeah, that's to answer your question there on the formulas. For example, this is actually you know, a fairly involved formula, and as you see, you find it here as a hint or as part of the question. So yeah, that happens frequently here. So you know, technically used, you know, suggested racks to use this formula to find the exponent n. Okay. Then you have to do the same for free space path loss. And yeah, and that's an example of open question. What would you use to improve the signal to interference ratio for these kind of systems? Okay, what are the tricks? It's a fairly open question. Okay, so typically I do expect 2 or 3 suggestions to cover the 6 marks, and I'll give you an example for that. So let's start with the 7 reuse here. So we go about that with a sort of a spiral, what they call a spiral pattern. You start from an hexagonal cell and you go around to cover the distribution in full. For example, if I put frequency 1 at the center, right, and then I go to, say, up to 2, then I do 3, 4, 5, 6, and 7 to form, again, a cluster. Okay? So you see that I started here, and I went up and sort of closed the loop in here. Okay? So this is the kind of pattern that you need to use here, called the spiral pattern. And concerning the part B, in here, okay, as you can see, already doing this very simple job here gets you 4 marks. Okay, in here, this tessellation is actually 4 marks out of 25 in here. Okay, B is asking you to assume first tier interferer. Okay, that gives you this formula and then calculate path loss n. So what we need to get to is n, you know, given SIR in dB, which is equal to 5. Okay. Now you need to remember you're given that the cell is hexagonal. Okay. Radius r and distance between hexagonal cell equal to d. Distance is the distance of the reuse. Okay, so here you have a distance of reuse 7, for example, right? And here you need to remember the simple relation here between dr and the reuse factor c. Okay. This is something that if you are prepared and you went through past papers, you need to have clear in mind. It's a simple formula. I'm going to write it down. D over R is actually equal to the square root of 3C, okay, for the hexagonal geometry. We went through a bit of demonstration in the lecture. You don't need to remember how to demonstrate that, but as an engineer, you need to remember the simple relations. Okay. So in our case, the reuse factor is 7. So we have D equal R. D over R equal to square root of 21 in here. So this leads to SIR approximately equal to 1 over, and I'm going to use the formula you're given as part of the question. You substitute that and the numerator in the denominator here, which is actually equal to square root of 21 minus 1 to the minus n here, plus square root of 21 plus 1 to the minus n, plus 4 times square root of 21 to the minus n again. This is actually the formula you need to invert. And the SIR in dB here needs to be transformed into linear units. SIR in linear units is 10 to the 5 over 10 here, which is equal to square root of 10 here, 10 to the 1/2 essentially. Okay, so that gives you left-hand member here. So eventually this boils down to be square root of 10 approximately equal to this ratio in here. Okay, so you need to go through that, need a bit. Okay, so you need to try essentially n. One way to go about that is to actually write down what the square root of 10 is in numbers, right? And it is actually approximately equal to 3.1623, right? And then you make a couple of trials for n here. Okay, you can try n equal 3, n equal 2, n equal 1. Okay. So if you, for example, if you try n equal 3, you can check that the SIR is approximately equal to 46, so it's definitely too far away from our 3.1623, right? So we go down, of course, and n equal to 1 is actually giving you an SIR of 3.82, okay, which is again pretty close now, right? So we have to confront those two numbers, okay? And here eventually, if you refine, okay, you can go to essentially fractional numbers for n, okay? So part of the game, to keep you busy 5-10 minutes during the exam, part of the game is to get you refining this n and find the most accurate number as possible in here. Okay, it doesn't have an enormous influence on the mark. For me, you've done, I'll talk about marks in a minute, but you've done all the job getting there in the right way. But now if you refine, you will find that the answer is n is actually included in 1.31 to 1.32 interval in here. So it's around this number that gives you the right answer, okay, if you do substitution in here. In terms of marks, yeah, remembering the formula here, the initial one is already 4 marks for me. In here. 4 out of 25. Sorry, I need to. Let me check the recording. It's going ahead well. Okay, 4 out of 25, I said. Oh, it's actually not working now. All right. So I got a problem with my annotation tool for some reason. Okay, then we have, so it's, yeah, essentially I can write it down on the other side. So it's 4 out of 25, as I said here, for the formula. Then I got the conversion in units there is actually 2 out of 25, so it's a passage that is fundamental, okay, from dB to linear units actually. So this formula here is 4, as I said, out of 25 here. Then you have, of course, this procedure of comparison here, of iteration, sort of trying to get to a refined n is worth 4 out of 25 in here. Okay? And this makes up a 10 in total for this, yes.
And for m, you said m minus 1, it would be 3.82. So obviously we should decrease m to get 3.46. So how come the answer is between?
Yeah, I suspect there is, I think it was too quick. There is some, actually that's a good exercise for you to do. Check for n equal 1 what number you get. You should have got a number that is lower than that, I presume, yeah. But if you do, I reported intermediate passages, but if you do this refinement job, you will find something like that. Okay, so probably shouldn't have put down those straight numbers.
Should we get the accurate number? Or
no, the one which is as close as possible, yeah. Just to show that you're getting there. So yeah, maybe verify this one. That's right, yeah. Okay, good. But the whole point is that you need to sort of try to satisfy this approximate equality. That's the whole point of this example. Yeah, then what you say is important also for part C, where you have to now do that for free space to find the SIR in free space. So in free space path loss, is n equal to, do you have any? So if I was to repeat the exercise in free space path loss, then I would know n. What would be n? Do you remember? The decay exponent for the power in free space.
E over d0 to the power of x.
Yeah, but what is gamma? That's the thing. Gamma here is n, right? In free space, what is that? How does it decay? Before it was in presence of a complex propagation environment, which led to this 1.3 weird one. But in free space, it's different. Exactly, yeah. N is actually equal to 2. Okay, the minus we peeled off in the formula. So n is actually equal to 2 in free space. So if I was to repeat that with the formula of SIR that I'm given as part of the question, that will lead to 12.87 in linear units. Okay? And this is actually the overall thing, is actually getting it right, is 3 out of 5. And this is actually 2 out of 5 to perform the substitution here in terms of marked distribution. Okay? Last thing, we have another part to cover here, which is part C. Sorry, that was part C actually, the part D, I mean. Which methods would you use to improve the signal to interference ratio for the system? It's an example of open question there. You have to think about the parameters that are involved in this formula. Okay, what are the parameters? Parameters are d over r, for example. Okay, and the signal to interference ratio is the signal power over the interference power coming from nearby users. So one thing that I actually thought is I can write it down. In order to improve the SIR, you can either reduce the amount of other user interference, okay, so you bring it down, the user interference, or you actually, what can you do in terms of d over r? In order to reduce the, to improve the signal to interference ratio. A straight answer may be increase or decrease d over r. That's already a very good one that may worth 6 marks. What do you need to do?
Decrease.
If you decrease,
Because the relationship is opposite.
yes, but you know, you need to think about the distance. D is the distance between the reuse, right? If you decrease, you bring the same frequency closer between cells. So actually it's the other way around. You have to increase the reuse distance or make the cell essentially larger. Okay,
Yeah, so increase the distance and decrease the R.
yeah, I would say the safe answer is increase d over r. Okay, increase d over r will actually give a higher, will give actually a better signal to interference ratio, but the counterpart is that you need a higher reuse factor, higher than 7. Okay, so if you put down something like that, just one, as I said, not a poem, just a couple of sentences, one sentence with the pros and the cons. That's already a very good answer. Okay, oops, pretty good. So I think we can stop it here. And yeah, now I know that one or two of you have questions, so if you can, in these last 15-20 minutes, approach me and try to answer those questions about project, if I understand correctly, or any other thing. All right, with that concludes the, really the module, and I wish you good luck with the exam and with the project for those of you who are MOC. Okay, but I'm sure you'll do a great job, as the coursework has been an excellent start this year. Okay? Thanks a lot.